I feel like actually like the prop pack. I didn't think they give you a lot more. So I'm going to show you. Also, everyone's there's no response. I said I see him now. Yeah. Can you get him? Oh, you okay? That's terrible.
My own order.
Yes, we can now. Yes, excellent.
Okay. All right. So I think we can start introducing you. So if you like,
Honestly.
all right. I will start then. Let's start introducing the speaker for today. In the meantime, I think everybody will be able to take some coffee. I see about 5-6 people going in there. All right. So today we have Jeff Moses from University of Cornell, not far from us. This morning, I understand. So that's pretty good. So Jeff did his bachelor from Yale University and a PhD at Cornell. He was his advisor was Frank White, same as advisor for our faculty member here. And then after finishing his PhD, he went to MIT, all good places, where he stayed 7 years working on ultra-short, ultra-fast phenomena, and joined the Cornell University in 2014, the School of Engineering and Applied Physics program there, where he's a professor now. And today he's telling us taking long-standing challenge in ultra-fast on the optics by a foreign but still physics. All right,
Well, thanks so much, Govind, for that introduction. It's really wonderful to be here. It's really always exciting to go somewhere where people are as crazy about optics as I am. And I've had some great conversations today. So I want to talk to you about some longstanding challenges I think are important challenges in ultrafast nonlinear optics. And let me start right in. I don't know if this clicker is working or not. No, I could use this. Okay, got it. So, of course, the most sort of common source of nonlinear optical phenomena interactions have been well described for about 60 years. You have an electric field incident on some materials, say it's a dielectric, and that field pulls electrons away from the equilibrium positions, and they feel the restoring force acting upon them. And if those displacements are large enough, then the electrons feel the nonlinear parts of the restoring force because it's an anharmonic potential. At second order, we get effects now in the polarizability that allow us to have sort of the products of electric fields contributing. So we get an order quadratic order in the restoring force. So we get three-wave mixing interactions where two fields can mix and give us the sums or differences in frequencies in terms of the polarization field frequency. At third order in the nonlinear restoring force, we get four-ways mixing. And this is where we, for the first time in terms of the nonlinear response, we can get polarization fields at the same frequency as the driving fields, and that gives rise to self-effects, like self-phase modulation. Now, of course, we know about these very basic things. They are behind so many different phenomena that we care about. And still, however, 60 years after the invention of the laser and the development of the field of nonlinear optics, which happened immediately afterwards, new applications of nonlinear optics continue to be discovered, and they're at the center of many still emerging technologies, and importantly, on many different scales. So this is how I start. When I give an overview of my work, I always start with these pictures these days, including this picture from Laboratory for Laser Energetics, which is very motivating to me. So from the third harmonic generation that's necessary to take intense infrared light to the UV, where it could be used for inertial confinement fusion, or at LLE, where OPCPA, or parametric amplification, is a key technology for creating the really short femtosecond pulses used there for study of laser fusion. Nonlinear optics comes into play is very important. And then, on a totally different scale, if there's going to be sort of a future quantum internet with quantum memories, communications channels, where there are different frequencies of light involved, we need ways of transferring information from one frequency to another. And we want to do that at low power, at the single photon level, and we want it to be extremely efficient. We want unitary operations. And then in the middle, we have a huge range of applications, from nonlinear spectroscopy and imaging, machining, where we want perhaps short pulses, intense light, and then sort of all sorts of different scales. Now, still though, however, over 60 years, there are many longstanding obstacles to these applications, and we run into the same things over and over again. In my work, I focus a lot on the constraints of the momentum matching condition. That is this relationship between what is the sort of the index of refraction of the interacting waves in wave mixing phenomena. If we have good wave matching, that ensures that the polarization field is going to emit light that's in phase with the light that's already traveling, and then we have coherent buildup and efficient transfer of power between different frequencies. But if this momentum matching condition is not satisfied, we end up with imperfect conversion. We have different cycles, periods in terms of this back conversion, and this gives rise to a really fundamental limitation, that is limited bandwidth, conversion bandwidth in these processes, and the efficiency bandwidth trade-off, because we have to propagate to a certain distance where we might only have good conversion for one particular color in sort of a sea of different colors that we have in our laser that we want to do something with. And then if we have nonlinearity and we have an inhomogeneous laser beam, because it's a real beam and it has a spatial extent and a temporal extent, then there's going to be inefficiency, right? We have intensity dependence, but we have a varying intensity. And then there's of course, the fundamental limitation that comes with the limited nonlinear response of materials. So it's sort of without much exception that from the visible out to the mid-infrared range, it's very hard to find a Chi2 susceptibility that's greater than a few tens of picometers per volt. Chi3 limited as well. And just one example, let's say we're trying to do frequency conversion by Chi2 in a microring resonator. If we had a much larger than typical nonlinearity, say 10 to the 4 picometers per volt, with a milliwatt of incident power, it would take a Q of about 10 to 3 to 10 to 4 to get full conversion. But at the level that we have in a good nonlinear material like lithium niobate, about 10 picometers per volt, then with a watt of power, we need a 10 to the 5 Q to get the same. thing. And so, it's a really important factor, of course, the strength of nonlinearity for applications. Okay, so in my group, we're kind of obsessed with these limitations and we're looking for ways to overcome them, especially when it comes to ultra short pulses. And I'm going to present today 3 methods that we've been exploring to try to overcome these. And these bring in some familiar physical concepts that are maybe unfamiliar for optics or nonlinear optics. So I'm going to talk about how we use an old trick of atomic physics, rapid adiabatic passage, for use in optical frequency conversion. And we've used this to perform now octospanning, dispersion-free up and down conversion without the normal efficiency bandwidth trade-off. I'm going to talk about how we use hybridized wave mixing, that is 3-wave mixing hybridized with second harmonic generation to achieve, well, to mimic the behavior of a lossy system without any real loss. We get oscillation damping and loss-like effects, like non-Hermitian physics-like effects in optics in a fully conservative system. And this allows us, I'll tell you, how we can make parametric amplification more efficient. It's a way for us to get around the spatiotemporal evolution inhomogeneity problem, which is an issue in a lot of nonlinear optics. Finally, I'm going to talk about how we get Raman scattering from coherent phonon coupling effects in materials and how this can lead to achieving some very strong optical nonlinearities. And really, I'm going to spend most of the talk talking about the first 2 of these. I'll have time just probably at the end to introduce you to that final topic. Okay. All right. So I'm going to be talking a lot about Chi2, 3-wave mixing, and I'm going to be talking about 2 different implementations, and it really depends on the initial conditions. So, we know about frequency up and down conversion, and I think the way this is usually implemented is we have a strong pump, and we have an input field, omega-1, and in the presence of the strong pump in the nonlinear crystal, we can shift that omega-1 up or down by the frequency omega-p. And this has been used for a lot of different applications in telecommunications. Now it's quantum information processing. This is an interesting method. It's used for upconversion sensing and imaging. The goal is to basically convert photons between this omega-1 and the omega-2. And so, for example, if we have mid-infrared light and we want to detect with a visible sensor, we can use upconversion for sensing or imaging, or we might want to start with a laser pulse that's broadband and then visible or near infrared and convert it to the mid-infrared for some application. Okay, so sort of getting into the basic description of the the translation of power between different waves. So we think of an omega-1 and omega-2 incident upon this medium, and we get if omega-1 is a high frequency, this splits up into an omega-2 and a new omega-3, which is at a difference frequency. And if we use the formalism of writing the field as a complex envelope and a wave that is oscillating at a kind of a center frequency, we could write this as basically a system of 3 differential equations that describes the coupling between the light. Now, if we use a certain constraint in our initial conditions, that we say that one of the low frequency waves is much stronger than the other 2. This is the setup of this up and down conversion type of application. This so-called strong pump condition basically ensures that we have a negligible relative change to that field 2. And so if that's the case, then we could treat it as a constant. And in that case, we have this 3-wave system that effectively we can describe as just a 2-equation system. Now, field 1, field 3 are basically sending photons back and forth, right? If we make a coordinate transformation, this system, particular system, can be written in this way, which you might recognize as exactly the way to describe a quantum 2-level system. Right, where now the coupling, that is the Rabi frequency on the off diagonals here, kappa, is proportional to the Chi2 susceptibility and the field strength of the pump, that field 2. And now our detuning would be this delta K parameter, which is the wave vector mismatch. So, going to furthering this quantum two-level system analogy, let me first mention, make it very clear that here our independent variable is propagation distance. It's not time as it would be normally in a Hamiltonian, a Schroeder equation description. Okay, so furthering this analogy, of course, Isaac Israel-Rabi in the 1930s did his pioneering work in describing nuclear magnetic resonance, which is the first description of a quantum two-level system coupled by some incident field. That description was to describe basically coupling in a spin 1/2 system, and the dynamics of these systems are population oscillations. So we have basically these so-called Rabi flopping cycles of going from the excitation state and back to the ground level state. And if the coupling field is not in resonance, if it's detuned, then basically we have a lower conversion. We have lower conversion to the excited state, and we have this faster period of oscillation. Okay, so because we can draw this mathematical analogy, we can now think of our frequency conversion as being just like Rabi flopping. That is, the conversion back conversion cycle that takes place between these different fields of different colors is really Rabi cycling. And when we have delta k equals 0, perfect phase matching, then we can have full conversion. When it's not the case, then we have lower conversion efficiency and we have a faster cycle period. And this is a way of now thinking about the efficiency the efficiency bandwidth trade-off and the limited bandwidth of conversion. Okay, it's like we have an inhomogeneous system of oscillators, and we're trying to convert them all with some laser that's only at one particular frequency. They're not all going to be converted equally. Okay, now Felix Bloch came along in the 1940s and synthesized the ideas of Rabi with Lev Landau and Zehner. The theory of adiabatic following and adiabatic passage, which says that if we slowly vary this detuning parameter, I don't know if you can see that anyway, but if you slowly vary this detuning parameter so that it slowly crosses 0, then the evolution looks very different. We have basically a small oscillation and population near the ground state, and then a quick inversion. So we have a full population inversion that then sort of asymptotically goes to full conversion, which was a great invention because it becomes a much more convenient way to have a precise preparation of some quantum state. Okay, you no longer have to exactly illuminate the system with a certain amount of intensity over a certain amount of time. Basically, you get this asymptotic approach. And we can think of this as kind of a strongly decoupled system, adiabatically changing to a strongly coupled one, and then coming back to a decoupled system again. Okay, so a great idea was put forward by Chaim Sukalski doing his PhD thesis with Yaron Silberberg in the late 2000s, that because this analogy exists, because the frequency conversion is just like Rabi flopping and is just like a quantum two-level system, where delta K is like the detuning parameter. Well, what if we take our ferroelectric domain poled crystal for quasi-phase matching and say lithium niobate, and where we have this effective momentum through the grading period, and we change that grading period longitudinally. Wasn't the first use of an aperiodic grading, but the observation made was that if this is a slow enough longitudinal change, then we can get adiabatic passage. And so this was the idea that basically now we have optical frequency conversion from one color to the other, where each color, as it passes through a certain period in this device, as it's traveling through, will meet some place where there's perfect phase matching. And this slow change, longitudinal change in the phase matching condition allows for rapid adiabatic passage. So all the different colors you put in as, say, a high frequency will end up as the new color in the low frequency part at a different position where it's phase matched. as long as the adiabatic condition is met. That is, the longitudinal change in the delta K is slow enough compared to the Rabi frequency squared, which means in this case, it's small enough compared to a factor that is proportional to the pump intensity. So this was a really cool idea. Here are some simulations of a particular application. First, looking at the case that we have a constant polling period. So this is the case where we expect just Rabi cycling type behavior. So these are simulations of, we have an incident 730 nanometer near infrared signal and a 1030 nanometer near infrared pump. This is a strong one. Phase matching between that gives conservation of energy between that gives us a 2500 nanometer mid-infrared. We might call it idler. And so here's basically the pseudocolor map of the conversion. We see that right at the phase match wavelength, we have this the slowest period and a full conversion to the mid-infrared. And then as we go away from perfect phase matching in either direction, we have the detuned Rabi flapping-like behavior. And we could look at this to understand the efficiency bandwidth trade-off. That is, if we cut off the crystal kind of early, we'll get a wider bandwidth, but a lower overall conversion, this red curve here. If we go to the point where we have peak conversion at the phase match wavelength, we have greater efficiency there, but we have that at the expense of lower conversion efficiency to other colors. So this gives rise to about a 50 nanometer bandwidth in this crystal that's about, cutting off at about 1.5 millimeters. So let's say instead we have the aperiodic grading, the longitudinally varying polling period. This is now a simulation of the same thing. This is a longer crystal. This is 20 millimeters now. And you'll see that all the different colors that we put in experience this rapid adiabatic passage-like dynamics, slightly different position in the material. And so, this is for one particular color. If I look though if I take this vertical cut, I see that I have high efficiency now for every single color. Now, you might look at this and say, you're not using the full capacity of the crystal, obviously. And so if I now come outwards in terms of the input wavelength here and the scale, you can see how it now works. Actually, this is the generated frequency. You see how we can convert a couple of octaves worth of bandwidth in one structure. So, we have this rapid adiabatic passage condition now taking place for all these different colors at different positions in the material. We have an octave spanning bandwidth. And in fact, what we're doing is we're coming close to being able to use the full capacity of the crystal to phase match, right? We're just, able to do it now for all the colors all at once. All right, so where I stepped into this field was to really work on these problems in ultrafast optics and see if we could use this adiabatic frequency conversion technique to make very short pulses of light. I do want to say there is a lot of literature in this field. There was a nice review written by Chaim Sikowski and others in 2014. More recently, I helped to write a review of the process for ultrafast applications. So the first experiment that I worked on was to take a titanium sapphire oscillator pulse that covers the full octave, an octave spanning oscillator, and to use an aperiodically pulled KTP crystal. The idea is to phase match basically this range here with the lower wavelengths. And this would produce, in the presence of a 1 micron pump pulse, an idler spectrum that looks like this dashed line. And what we measured was the solid line, and our measurement was limited by our in-gas spectrometer that we used. And looking at the photodiode response or the conversion efficiency in the mid-infrared as a function of the incident pump intensity, we saw exactly what's expected for an adiabatic transition, where basically if we go above a certain threshold intensity for the pump, we're getting full conversion. So that was a nice demonstration. And one thing you can see here is that there's a one-to-one correspondence in the power spectrum. We have this amplitude transfer from the near infrared to the mid infrared. And this was something that we also found when we changed the experiment slightly. Now, to accommodate a broader bandwidth using a lithium niobate crystal, we use higher energy pulses from an OPCPA. And we showed that with this input spectrum, we could convert light all the way from about 2 to almost 5 microns. And we get this sort of one-to-one transfer, every photon we put in, we get a photon out, or nearly 1 photon out for every photon we put in. Okay. So one nice thing about this down conversion method, and especially when we're using a relatively narrowband pump, is that if we are considering what the difference frequency spectrum looks like, if we have this sort of square spectrum in the photon count, we're going to get a photon subtracted, everything in here, all the photons across the whole spectrum. We get a new ones over here where we're just subtracting out this pump frequency. And so what we're doing is we're in effect preserving the absolute bandwidth, but the center frequency is getting smaller, and so the relative bandwidth is increasing. Another way of putting this is that a 10 femtosecond pulse in the near infrared, if we preserve the absolute bandwidth, in the mid infrared, we still support a 10 femtosecond pulse, but this is now supporting a 1-cycle pulse rather than a 4-cycle pulse. So this becomes a really nice way to generate a huge spectrum in the mid infrared. And one more thing is that under these conditions, not only do we expect a linear amplitude transfer function from the high frequency to low frequency, but we expect a linear phase transfer function. And this is something that we took advantage of in a next experiment. And we were thinking, okay, this is kind of a nice opportunity for applications in which we want not only to generate a broad mid-infrared bandwidth, but we want to shape that bandwidth. It's hard to shape bandwidth when it's octave spanning. So the idea is we use a near-infrared laser, we use some near-infrared pulse shaper, then we use this adiabatic frequency conversion technique to convert to mid-infrared, and we end up with a shaped octave-spanning mid-infrared pulse. And so the experiment we did was just to put a pulse shaper that's in the OPCPA system that generated the near-infrared pulse, recombine this near-infrared pulse with some of the pump laser we used before frequency doubling it to pump this OPCPA. We had 12 picosecond pump pulses, about 100 microjoule energy at 1 micron wavelength. We combined this with a broadband chirped pulse in the near infrared. This goes through this adiabatic difference frequency generation process. And to attune the pulse shaper to have exactly the right phase at the start, that we would manage the dispersion to have a compressed pulse after a bulk silicon compressor, which has normal dispersion in the mid-infrared. So we did this successfully. We were able to tune this pulse shaper that we were able to get all the different frequency components in phase. So what we got out at the end was indeed a single cycle pulse in the mid-infrared with about a microjoule of energy. So the next thing we did, thinking about trying to now shape pulses that have this huge bandwidth, is that we dialed in the pulse shaper now an additional phase and amplitude modulation in the spectral domain that would create a double pulse input. And this is a double pulse also with a chirp on it. This is converted over, becomes de-chirped, and becomes a double pulse now, basically 2 single cycle pulses now with a delay between the pulses that can be controlled with the pulse shaper. Okay, so we are excited about this result, and it's sort of motivating some ideas for how we do ultrafast spectroscopy, where we might want, say, a double pulse sequence for multidimensional spectroscopy. Okay, so we were still thinking about this more though, because this was a very complicated system. And we were trying to understand, where does the dispersion come from in this setup? And well, it comes from all the usual dispersive elements that we have in the system, but there's also the dispersion from the device itself. And this intrinsic dispersion can be thought of as due to the fact, well, that we have material dispersion from the lithium niobate, say, but part of the propagation distance in the material, we have propagation of a near-infrared pulse, and then we have conversion, and then it continues to propagate as a mid-infrared pulse. But the position in which that transition takes place is different for each color. And so we have this function, we can call it Z sub C as a function of frequency. This is where this sort of rapid adiabatic passage is taking place. And we could write the group delay as just being kind of the group delay that experiences the near infrared pulse for the first part, followed by the group delay it experiences the mid infrared for the second part. So this actually worked really well in terms of this analytical formula that we could derive from first principles, but that against pulse propagation simulations. And so we were thinking about this more, and the fact that we have really this monstrous dispersion management system where, well, first of all, here it is, the adiabatic DFG crystal had not that much GVD actually, but a huge third order dispersion. And we had all these other elements here in order to take care of the dispersion management. Some people in this room really understand the pain of this, right? Especially when you get to such a huge bandwidth. So the idea was, okay, can we tailor this line here so that we can change the group delay dispersion and to our advantage? Okay, and this is a concept of using an aperiodically polled quasi-phase matching device to control the dispersion you have that started long before we got to it, but different work done by different groups. Marty Fayer was involved in this. Amadis Galinauskas, so a bunch of people looking at sort of different systems and how one can use aperiodic gratings to basically tailor dispersion. So we set out to do this now and preserve this adiabatic frequency conversion. So here was actually what we set out to do. So the idea was we have now a compressed, let's say that we have coming out of our system, we've gone to all this work to make a compressed pulse in the near infrared that's very short. What we want to do is now we want to create a compressed pulse in the mid infrared that's also short. So the question is, can we design this grating that it compensates its own dispersion so that basically we don't have any additional work to do? We put in a 10 femtosecond pulse in the near infrared, we get a 10 femtosecond pulse out in the mid infrared. So my student worked on this and didn't take long to sort of change a little bit. This is not a linear change in the polling period, and come up with a function that would indeed allow us to do this. And this is the device he came up with, and he simulated it. And basically, here's the 10 femtosecond pulse coming in. What happens is there's a large expanse here where the dispersion of the lithium niobate is chirping that near infrared pulse. Then at some position about 11 millimeters in, some of those frequencies get converted over the mid infrared, and is designed just so that all of these frequencies catch up in terms of the group delay at the end of the device. Okay. So this was a concept and design from a while back, and it took us a while to get devices that we weren't destroying and a laser that was working well enough. But my students were able to come through. Here's actually a look at the design again. So this was a linear. This is what a linearly. So if we have a linear function of polling period with longitudinal distance. This is the group. This is basically the dispersion of the group delay that we'd have. It's about 5 picoseconds from one extreme to the other. With our new design, it looks like a flat line on that scale, and we have only about a 10 to 20 femtosecond net, full span of group delay. And the simulation said, indeed, if we put a 10 femtosecond pulse in under these conditions, we get a 10 femtosecond pulse out. Okay, so we were able to do experiments earlier this year that finally verified this. So basically, my student worked really hard to compress and characterize an 11 femtosecond pulse using a frog setup. Then this pulse was combined with a 7 picosecond 1030 nanometer pump pulse in the design crystal, and then we just characterize the output. It's as simple as that. And this is what we found. 11 femtosecond pulse in the near infrared in could produce a mid infrared pulse out. Here in orange is basically the group delay dispersion function that we were able to extract from the measurements, indeed mostly flat with some ripples. This is due to an absorption line. So there's a little bit of a parasitic effect here from sort of unintended wave mixing that we have in the system. That had to do with this initial section of the device where it was only chirping the pulse in the near infrared. It was all the same polling period, and there was a parasitic wave mixing process that was moving light from over here to over here, something that we could avoid in a future iteration. But it did work extremely well. This is characterized by a technique called FROST, frequency resolved optical switching, that Francois Legore's group came up with. It's like FROG, where the gating is done by a transient absorption response. So you have a reference pulse that emits free carriers in a thin semiconductor, and that actually acts to block all the light that comes and the pulse you're testing after that gating pulse. It's slicing it with like a step function in time. Okay, so so the outlook in my group, and we're interested in some ultrafast spectroscopy measurements. We're interested in some ultrafast induced dynamics in molecules, for example. What we're trying to do is come up with basically a whole bunch of different 10 femtosecond pulses from visible through mid-infrared. The idea is you work really hard to make that one pulse in the near-infrared, and then you use these different stages to get your short pulse at the other wavelengths. All right, now one more thing that we did is to look whether we could do this not just with 3-wave mixing, but with 4-wave mixing. The idea being, it'd be nice to use something other than a quasi-phase matched material to do this. And indeed, this way of describing this 3-wave mixing system can be used for a 4-wave mixing system too, what is often called 4-wave mixing Bragg scattering, where this is basically a degenerate 4-wave mixing experiment where we have 2 strong pumps now. And the idea is still then we have basically a quasi 2-level system for the weaker fields. And we could describe this in the same way, just now this kappa is proportional to chi3 and the field amplitude of both of these 2 different pumps. And the question is, how do we get the longitudinal change in delta K? And so we were thinking about different ideas, and this work is a collaboration between my group and Chaim Sakowski's group. We did some theory, both looking at some silicon waveguide structures, and in my group, we were more sort of looking at fibers. So we could use, for example, a tapered fiber, or say a hollow fiber with a pressure gradient in it as a way to get a wave vector mismatch that changes longitudinally. And my group did an experiment collaborating with Tim Burke's group at University of Bath. They provided us with a tapered highly nonlinear small core PCF fiber. So it over just a few centimeters, we have a core diameter taper range from about 4.2 to 3.6 microns. And here's the phase matching diagrams for different signal wavelengths. These are different mid-infrared Eidler wavelengths we get out with phase matching happening at different core diameter. So this is a more complicated experiment in the sense that we need 2 pump beams now. We used a 1 micron pump, and it's doubled frequency at 515. And we mix that together with 700 to 740 nanometer light in this tapered PCF fiber. It took my student a while to align this, but he persevered and did measurements of the Eidler light. And so here's actually what a simulation says we should get if we have an untapered fiber. That's where delta K is steady longitudinally. So we should have the typical Rabi flopping dynamics. And this is actually what the simulation says, although there's a little bit of a blue shifting effect due to cross-phase modulation with some temporal walk-off between pulses. And here is what we measured in the experiment in blue compared against what the simulation says we should get. When we switched to the tapered PCF, we were able to, the simulation has this profile we expect for adiabatic conversion with these different colors converting at different longitudinal coordinates. And the experiment and the simulation matched pretty well in terms of what we got out. We also did some measurements, some other measurements to that I guess I didn't insert the plots here, but to verify that we had adiabatic passage like a conversion. And what we're doing now is we're looking into other fibers where we might have some advantages in terms of applications. So, for example, a hollow fiber, right? If the nonlinear conversion is taking place in gas, then we can accommodate much higher power. We have a much larger core, so we can scale this to higher energies. And in anti-resonant hollow core fiber, we also have, there's a little bit of a trade-off. You can't get quite as large cores as capillary fibers, but you have real wave guiding, and you can structure and tailor the dispersion with the design of that fiber. Some simulations we published a couple of years ago suggest that we could use something like this 7-ring revolver type of anti-resonant hollow core fiber to do a near octave spanning conversion to the mid-infrared with higher pulse energy. Okay, so this is about as far as I wanted to go on this topic, and I'm just checking the time here. I want to switch gears a little bit now and talk about another very important application of frequency conversion, but now the application of parametric amplification, where the idea is not just to translate photons from one color to another color, but to actually have amplification where we take this pump beam in a weak signal. And the idea here, of course, is to transfer as much power as possible to the desired wave. For example, so we transfer power to the signal and we want to convert as many photons as we pump over. So OPA, although it's an extremely important tool for extending powerful lasers to other colors, does have the trade-off that it's inefficient. It's an inefficient amplifier in the sense that typically you lose about an order of magnitude of power. And there are two reasons due to this. One is the fact that what we call the quantum defect, the fact that the photon in the pump is splitting up into two different photons, and we only care about one of them, and so we're not getting as much energy in the photon we care about as the one that we put in the pump. And this is especially harmful if we're converting to a much longer wavelength, and the quantum defect is low. But there's another issue, and that is poor pump conversion. That is, only 10 to 30% of the pump photons actually get converted over from the pump to the signal in idler. And these two things combined means that if we are converting, say, near-infrared to near-infrared, maybe we'll get 10 to 20% conversion at best. If we're going from near-infrared all the way to mid-infrared, it might be more like a few percent conversion. And there are a lot of reasons to be excited today about having brighter, ultrafast mid-infrared pulses. I think a lot of people here probably work on mid-infrared applications or sources, from basically high harmonic generation using a longer wavelength driver sources to get to higher energy photons, reaching sort of the keV range, to precision and ultrafast spectroscopy, being able to look at the composition of things through their molecular fingerprints, or understand how vibrational dynamics coupled to electronic dynamics in systems using sort of multidimensional spectroscopy. There's an active field now at changing the properties of quantum materials by driving them hard with IR light. And a lot of excitement there. And then there are also there's a lot of interest because of atmospheric applications, because of the very wide transmission windows in the mid-wave and long-wave infrared. So, more motivation for this is the fact that today there are powerful diode pump solid-state lasers increasing, every year in terms of average power and the pulse energy they can put out. Here's an example from Jorge Roca's group at Colorado State. This is a 1 joule, 1 kilohertz. That is a kilowatt laser system making 4 picosecond pulses at 1 micron, cryokilodetrubium YAG. Here's a laser based on holmium YILF at 2 micron wavelength, a couple hundred millijoules, 100 hertz. This is from Jens Biegert's group in Barcelona. Now, in this case, this 2 micron source was used as a pump source for an OPA, producing 7 micron light. And in this case, about 22 millijoules down to about 3/4 of a millijoule, 3.5% conversion efficiency. And I put this up as a really nice result, because that is actually a very good conversion efficiency for OPA going to such a long, so much longer a wavelength. So the question is, can we do better? So here's now going back to sort of the fundamental dynamics, where the problem lies, and how we're trying to address it. So in this case, what we do is we start with all these photons in the pump high frequency, and these flip to signal in idler. And so in an optical parametric amplifier, you have the pump diminishing exponentially and the signal in idler growing exponentially. But then as you deplete the pump, you get the reciprocal process, the some frequency generation, because you have strong polarization now at the some frequency field after you depleted all the pump. And so there's now a reversal in dynamics, and you have this conversion back conversion cycle. So this is actually a big part of the issue why OPA is inefficient. And it's because if we look at the different intensities of the pump in space or time, it's a beam and it's a pulse, right? Basically the rate of this conversion back conversion cycle is different. Actually, the way the mathematics works, it's like one can think of this as basically a harmonic, well, it's an anharmonic oscillator, but it's an oscillator where time elapses at a different rate for the different points along this pump beam. And so what happens is that as the pump intensity is being depleted, it's fully depleted at different lengths at different coordinates. So as I sort of go along, I start to see depletion at the center, full depletion at the center, but I still don't have much happening at the wings of the profile. If I continue, then I can have better efficiency at the wings, but at the expense of the center because of the back conversion. And if one looks at this over the full range, this kind of optimal result actually coincides roughly with where we have full depletion at the center. So, what calculations say is that if you have a high gain amplifier, you only have about 10% quantum efficiency. That is, only 10% of the pump photons can be converted over to signal idler at a time. And that's because this is happening in 3 dimensions, 3 transverse dimensions. Here's the picture that I was talking about. So this is really like an anharmonic oscillator, like a sink basin, okay, where you have marbles rolling down. You let them all go down at the same time, but the time elapses at a different rate for each one, and so basically they're not going to fall down at the bottom all at the same time. Okay. All right. So this results in poor conversion efficiency, and actually, if we look at it more carefully, in fact, the ideal conversion efficiency looks like this. But we go a little bit deeper in, so we have almost full back conversion at the center. It's actually where we get the greatest conversion efficiency. But for most applications, we don't want the kind of spherical shell and space and time that you get from that. Most people want a singly peaked beam and pulse. And to do that, the best you can do in this simulation, which is about 10 to the 4 gain, is 12% pump to signal energy transfer. So this corresponds to this, what I call practical limit, whereas this I call the extraction limit, nowhere near what we call the quantum defect limit. That is, every pump photon is being converted over to the signal idler. All right, so there are ways to deal with this. One was pioneered at LLE, which is basically you have you shape your pump so it's flat top. So if you have the same pump intensity everywhere, then you don't have this issue. But this fantastic result from LLE back in early 2000s, 34% conversion. I hear it's even higher today. But having very large energetic beams makes it easier to shape to high order super Gaussian. And then having also nanosecond pulse durations also makes it easier to do this in time. You could use now basically electronics to do your filtering versus time in order to create a flat top pulse. Another thing that one can do, this is something I actually worked on earlier, if you're thinking about OPCPA, where you have different frequencies at different times, you can use the sort of conformal pulse shaping theory where because of the wave vector mismatch and the difference in seed intensity, there's an ideal pump intensity that you could use to get the conversion cycles to line up at all points along the temporal extent of the interaction. And so in this case, this kind of red, almost Batman shaped pulse would be ideal. But, the problem is that for common applications, the shaping itself imparts too much loss, and so it becomes impractical. And so I don't think anyone has demonstrated anything like this that we predicted in our theory paper a bunch of years ago. Okay, so here's another picture now in terms of the photon change dynamics. I actually don't know what time it is. I've got...
we still have about 10 minutes, 10 to 12 minutes.
10 to 12 minutes, okay, great. So let's say that we have all these pump photons, a few signal photons, and what's going to happen is that each pump photon splits into signal and idler, and there are these Manley-Rowe relations we can derive that describe conserved quantities in terms of photon numbers. So for every pump photon I convert over, I get 1 in the signal, and I also get 1 in the idler. And this continues repeatedly until I fully deplete my bucket of pump photons. And then the reverse happens because we have this polarization field that's very strong at the pump frequency, which is a product of the either and signal frequencies, and we get the reversal of this, and we get creation of pump photons. So a really cool idea was put forward about 7 years ago now by a group in Shanghai, that what if we have concurrent loss of the idler field? So that is, the idler photons is like we have a tap on our idler bucket, and these idler photons are going away as they're being generated. Well, then, the signal photon would like to reconvert over to the pump, but it doesn't have its idler buddy, and it can't get there. So this was demonstrated to great success. So what this group did, and this is a group actually that cares about very high energy lasers, high peak power lasers. They basically they fabricated a YCOB crystal with a dopant, the samarium dopant, that has this profile of absorption that looks like this. In this case, their pump and their signal produced an idler around telecom wavelengths that had the right amount of absorption to make this work for extremely well for sort of a low gain amplifier. So they actually achieved over 40% energy conversion to the signal by this approach. So we were thinking about this and we were thinking, okay, so ideally, especially if we want to use this for high average power systems, right? And we have all this great growth in high average power laser systems. Ideally, we wouldn't have any absorption in the material because we don't want thermal loading. In fact, very often we switch to parametric amplification versus lasers because we don't want thermal loading. So we'd like a fully parametric or conservative process. We'd also like flexible choice of way of the material. It would be great if we didn't have to fabricate a specialized material for each application. And also it would be nice if we could reuse the energy that we convert over to the idler. So here was the idea, a very simple one. What if we could simultaneously phase match second harmonic generation of the idler field, so another nonlinear process instead of a linear process? So every two idler photons come together and produce an idler second harmonic. And now basically we change our Manley-Rowe conditions so we can have basically loss to this idler second harmonic field. And you know, an interesting thing is that second harmonic generation, when it's phase matched, you know, a lot of this, this result for perfectly phase matched second harmonic generation. Oh, I don't have it on the next slide. I had a few slides forward, but it goes only in one direction. There's no back conversion. So if there's no back conversion, then how is it different than loss to an incoherent bath, right? I mean, that's the property of an incoherent bath, right? The entropy makes things go in one direction only. So first thing that we did, of course, was we did simulations, we modeled this thing. And what we're doing is now we're adding as a new channel for light for the idler to go now to its second harmonic. So we have to add some additional terms and another equation to keep track of the idler second harmonic field. And looking at this equation now for the idler, you'll see that what you have is a gain term here and you have a loss term now. And you can convince yourself looking at this that the loss term cannot become significant until we have significant transfer from pump to signal and idler, okay? And that's exactly what the simulations show. So basically it starts out like a normal parametric amplifier, but when we have significant pump depletion and significant growth of the idler, then we start to see idler second harmonic generation. And it's because we don't have back conversion of the second harmonic field. This happens kind of in a piecewise fashion so that we have what looks like a damped oscillator now. Okay, and okay, I was making this point before that second harmonic generation is different from the normal case of three-wave mixing in that if it's perfectly phase matched, there's no back conversion. It's essentially unidirectional. And you know, then how is it any different in terms of its, what it's doing from an incoherent bath? And in fact, my really bright student, Noah, said, well, maybe we can model this as a non-Hermitian system, even though it is conservative. I'll only talk about this for a second, but this is something that we just got published. So, many of us are familiar with the sort of the model system of coupled waveguides, right, where we have kind of a loss channel. And I guess I should go here first. So analyzing this in a gauge transform frame where we have balance, gain, and loss, one can find these special properties of non-Hermitian systems that involve, basically they're open, they involve some loss of what so-called exceptional points and parity time symmetry breaking. There's a big field in optics that are looking at the special properties around such devices under these conditions. Well, in our system, what we have is basically a pump photon splits into a signal and an idler by three-wave mixing. And then we have this loss channel, effective loss channel for the idler divided second harmonic. If we look at just this two-mode subsystem, basically exchange between pump and idler, it looks a lot like the coupled waveguide system. It's a nonlinear coupling. And the loss is by another nonlinear process, but we could also go to a gauge transform frame and look at this as a balance, gain, and loss, and we can find the same sort of behaviors involving. In fact, what our paper shows is that there are exceptional points for this two-mode subsystem, PT symmetry breaking, and that behavior, due to the non-Hermitian physics, actually carries into the other fields, which is so it becomes a way of now putting essentially, it's loss-like behavior. We're now injecting that into a conservative system. And, that's maybe an idea that, could inspire something else. So, okay, so why is this good? So now all these different points along the pump pulse have these different evolution profiles where we have not full conversion back conversion, but damped back conversion. And that means that as we move along, we start getting the same thing we had in the normal OPA, but we have damped back conversion. And so as we move along, more and more of this profile is basically filling out in terms of its conversion from pump to signal. And here, if we now look at sort of walking through the exchange, the optimal result now is all the way at the end here, where all these different oscillation cycles have damped out, and we have nearly full pump extraction. Okay, here's some nice simulations done by undergraduate in our group, Adam Zertea, of the 4-field dynamics. So here you see basically the pump. You can see the conversion these cycles damping out and conversion moving basically from inside out. You have the inverse process for the signal, which is like the photon count is 1 minus the pump. And we see this stepwise increase in the either second harmonic. And now going back to this kind of applications look at it and sort of the limits and conversion, for the case where we mix in the second harmonic generation, and we call this, like we're calling this hybridized parametric amplification, or HPA, appears on the slides sometimes. So now what happens is we go further and further in propagation, we get more and more conversion, and we get to a point where we're actually starting to approach the full quantum efficiency, and we're doing much better than the OPA case. Okay. Okay, so you might be thinking, well, great, that's really cute, but how are you going to phase match this? Well, okay, so it turns out that it's not as bad a problem as you would imagine. There's an additional constraint, okay, but even with birefringent phase matching, one can get it to work. And basically, I had another undergrad who's really good, Devin Dean, working on this problem. And for non-collinear phase matching, what we do is we say, okay, the idler is going to be phase matched with a certain theta angle. For a uniaxial crystal, let's say, in type 1 phase matching, we're going to have a particular angle where we have phase matching of that. And then basically, for a given frequency of pump, we basically scan this non-collinear angle until we get the phase matching to work for the OPA as well. And it turns out there are 2 solutions generally. And if we scan the signal wavelength for a fixed pump, basically we have a different constraint on the non-collinear angle. But it turns out that solutions exist for common pump laser wavelengths and in ordinary nonlinear crystals. This is, for example, a 1030 nanometer pump in lithium niobate. So our trial experiment was designed like this. We said, okay, what if we have a 1 watt, a 2 micron laser, and our goal is to make something like a 0.5 watt, 3 micron laser. So can we get to about 50% conversion using this hybridized process? This is like, what we do, we didn't have a holmium laser, but it would be like, let's say that we have a nice holmium laser and we want to convert this to 3 micron. So we collaborated with Pete Schuneman and Kevin Zawilski from BAE Systems. They have pioneered a lot of mid-infrared nonlinear crystals, including the CSP crystal. And this is kind of a less well-known nonlinear crystal that has a nice broad transparency range from about 500 nanometers out to about 7 microns. But I want to say it's not a special crystal it's not like a totally different thing than most crystals. It's like lithium niobate for the mid-infrared. You might say it's got a good nonlinear coefficient, got a good transparency range, but there's nothing magical about this crystal otherwise. So phase matching works for this. So here's this non-collinear angle chart. We chose to do this with a close to non-collinear angle. We had about a 0.5 degree non-collinear angle with, we had a 2.2 micron pump from an OPA, a 3.4 micron signal. We had about picosecond duration here. And we combined these almost collinearly with the Rokon prism, and then we looked at the amplified signal, residual pump, the either second harmonic. Here's the signal, here's the either second harmonic frequencies. And so what I want to show you first is what the pump depletion looks like. So this is now using a microbolometer imager, and basically each frame is normalized to the increased pump power. So it's like we're watching how much of the pump is being depleted out, right, with a normalized top to it. So we can see the effect on the shape. And you see basically that we're getting the sort of behavior that you would expect. That is, it basically depletes at the center and there's this sort of little bit of back conversion, but that's damped out and you get these ripples that are sort of migrating outwards. All right, here's a look against the simulations. And when my students showed me this, I was like, wow, because it works really well. Okay. And, you could see all these sort of rippling effects and it's really coinciding very well. And of course, what was really important though is how it worked in terms of conversion efficiency. So here I'm showing you in red, these are OPA simulations. In black, it's this hybridized parametric amplifier simulations, and in blue is what we actually measured. Here was the signal beam that we obtained at the end, and we got to 68% quantum efficiency or 44% pump to signal energy conversion. And another remarkable thing about this is this was almost 5 orders of magnitude of gain. So this problem due to spatial temporal inhomogeneity is worse when you go to higher gain. It's like worse gain narrowing is one way you could think of it. And so this also has a nice practical consequence because now we could use a single stage amplifier to do efficient amplification. So it also helps to sort of resolve one of the issues with parametric amplifiers is that they're quite complicated also when you actually build it, right? Preamplifiers, power amplifiers. Okay, so one more thing to point out in terms of, so here's the simulated pump depletion for the hybridized system. Here's the normal OPA. Here's what we got. And it really matches this well. But you may have noticed this little bump that's coming up at the end. Now we were limited to 1 watt pump power. We didn't go beyond that, but this looks like back conversion, right? And so, we understood that this should happen earlier on from our simulations, but the issue is that phase mismatch is really unavoidable. There's no such thing as a perfectly phase matched system for a real laser beam, right? You have if you have a Gaussian beam, you have a distribution of wave vectors, not all of them are at the right angle, right? And you also have a pulse and you have different frequencies, not all of them are perfectly phase matched. So phase mismatch is unavoidable, and what happens with phase mismatch is that you get an eventual reversal of the dynamics. So you have a damped oscillator, and then you have a damped growth back up. And you see this both with delta K not being non-zero for the second harmonic generation and OPA. And in fact, you can get them to sort of cancel each other out a little bit. But basically what you're seeing here is that after a certain distance, you start to see the effects of the wave vector mismatch. Other things can play into it, like walk off in time and space can also disturb the dynamics. But the cool thing is that we can go far enough before this back conversion takes place that we get almost everything converted, right? And that really becomes the limitation. These were simulations, and of course we're doing much better than the OPA case. Oh, and sort of this is what my undergrad was really after, seeing what range of different frequencies should this work with in terms of birefringent phase matching, and it actually looks pretty good for a lot of common laser wavelengths, a lot of common crystals. For doing frequency conversion and OPA. The gray bars are phase matching tuning ranges for OPA, and the colored ones are what we predict are the tuning ranges for this hybridized process, when we also take into account practical issues like not wanting too large a non-collinear angle, for example, like greater than 4 degrees. Okay, one more thing about the dynamics before I move on. So
we're sort of out of time now, just to let you know that they're
okay.
So
a
couple of minutes to wrap up, I guess.
Okay, I apologize.
We'll likely some time for questions.
Okay, thank you. I'm sorry. So basically, the fact that this is a damped oscillator is a really nice mathematics to describe that. So this is the case with linear loss. This is the case with Euler's second harmonic generation loss. Really, for an OPA is an undamped anharmonic oscillator, right? And what we have here is the apparent oscillation damping, and in fact, you can derive a master equation for the evolution of the pump field by combining differential equations for the different fields and also using the Manley-Rowe conditions. And in fact, what you have here is a nonlinear oscillator, an anharmonic oscillator with a damping term, a first derivative term. And the damping coefficient is either the absorption coefficient of the linear loss process, or is this coefficient that depends on the amount of photons that are displaced to the second harmonic field. Not only that, but that coefficient depends on the frequencies that are involved, because actually it's related to the drive strength of the second harmonic generation versus the OPA process, which is really for a lossless material that depends on really just the ratio of frequencies. But we can have underdamped, critically damped, and overdamped behavior. This might be kind of advantageous from an applications perspective. This is sort of the shortest length to get full conversion. And that was really nice. And one other thing that we're excited about is cascading these sort of stages, so that because in the case that twice the Euler frequency is greater than the signal, and now it's higher frequency than the pump, we could actually use that remaining power in the Euler second harmonic as a new pump. And in fact, something like this is particularly attractive where, so this is one of the things that we want to try to do next. So we could do an experiment where we actually have degenerate OPA, but it's non-collinear. And so the Euler second harmonic now comes out at a different angle, but is the same wavelength as the original pump, and use that to amplify again. The idea here is that we could actually potentially get to a point where we have more than one signal photon coming out for every pump photon. And in fact, if we had a quantum efficiency, we had 68% is what we measured in our device. If you get to 70% with 3 stages like this, you can actually beat the quantum defect from it. So, that would be cool. We'll see. All right. So I'm out of time, and I guess I shouldn't take more of your time. So I can't go into the Raman scattering effect. I'll just say, sort of summarize a little bit very quickly that we looked at what happens if Raman scattering happens on an infrared resonance in a crystal where we have IR phonons and Raman phonons. And what we found is that normally what Raman scattering is we can think of it, so one can't directly drive a Raman phonon with light because it doesn't carry a dipole moment. But Raman scattering comes about, we know, because we can describe the polarizability, the electronic polarizability is depending on the Raman phonon's displacement. And so we can think of basically a contribution to the electric susceptibility that depends on a Raman phonon displacement. And so what we ended up looking at was a case where our dipole is not the electronic dipole of a system, but from an IR phonon. So and how the IR phonon's polarizability is affected by the Raman phonon displacement. And it turns out that one can get a very strong dependence of the IR susceptibility on this, and not only that, but if you're resonantly driving the IR phonon, I got to skip a few things here. But I didn't get to. But we find that we can get extremely strong optical nonlinearities from this Raman scattering process. This is something we published last year. What we found is in the terahertz range, we get Stokes and anti-Stokes peaks with a chi3 that's about 10 to the minus 15 meters squared per volt squared. So about 7 orders of magnitude greater than sort of the normal chi3 or Kerr effect, near infrared wavelengths. We found that very high nonlinearities persist even at very large high frequencies. So we got very strong cross-phase modulation type effects. Okay, so sorry for going late. I have a whole bunch of people to thank for this work, especially the people here in Bold Phase, our collaborators, and their funding. Thanks for your attention.
A few questions I get. I wanted by that the field in the OPA process. Is there a way you can blend the two together? Does that give you degrees of freedom in high efficiency OPAs?
That's a really interesting question. I haven't thought about that, Jake. So there has been a lot of work on OPA with an adiabatic change in the wave vector parameter. So Marty Fayer's group did a lot of work on this, and Ursula Keller's group did work on this. It's not exactly the same. It's not, you don't have the direct analogy of a column 2-level system. You can improve both efficiency and bandwidth. So you definitely win out by doing this in a quasi-phase matching device, but you don't fully get rid of the trade-off between efficiency and bandwidth. You're asking, what if we take something like that and we add hydro loss to the picture? Will that help? That's a really cool question. I haven't thought about it. And maybe one could, yeah.
Anything else? Okay.
So you were talking about the idler SHG, right? Why wouldn't that, shop back to the mix back with the pump, right? Why wouldn't there be more?
Yeah, so it's if going back to just the basic description of this, if you go back to the early 1960s papers by Bloomberg and others describing the evolution behavior of wave mixing, you find with the sort of initial conditions of second harmonic generation, it takes a different form. It doesn't go back, it continues on. The way to think about this physically is, slide.
I mean, maybe I was actually asking about the SAG beam talking to the original pump. Not.
Oh, I see what you're saying. Because it's not phase matched. Yeah. So there will be there could be a polarization if wavelengths end up working out. And in fact, you could think of the scenario where you have something going on like double the Euler frequency is one of the other fields, and that might create some weird things going on. But unless you pick exactly the right frequencies and have like conservation of energy makes them overlap, and you have phase matching for the process, then it wouldn't matter. Yeah. You need both of those to happen.
Yeah, the fact that you do eventually start getting some of this back action on the pump after the long period of time.
Yeah.
Is that sort of a residual consequence of the fact that it's still a conservative system?
That's
I mean, the fact that you're not really
well.
getting
Yeah, I mean,
rid of the Euler photons.
yeah, I mean, definitely you're right in that you have this co-propagating Euler second harmonic field, and it is constantly participating in shaking the electrons, right? It's actually doing its thing, so that's always a danger, yeah, because you're never actually removing it from the system. Foremost, what is going wrong is that it's not actually perfectly phase matched, right? Or if you have walk off and your beams are moving apart a little bit, let's say, then you're disturbing these nice dynamics that are happening. You're putting photons back in, right, where they shouldn't be, for example. But yeah, I'd agree with that statement.
There's a question online from Vitek. Do you want to go ahead with that?
Yes. So you talked about the cascading the
We
process.
can't hear you. Are you?
Can't you hear me?
Yes.
Hello?
Try again.
Maybe we don't have a sound.
No, I think we don't have a sound here. You want to type on the chat? I can read it.
Can you hear me now?
No, there's no sound coming here.
Okay.
We can't hear you. Okay, I guess anything from here? Go ahead.
Yeah, so you mentioned that the linear chirp for the polling period, it didn't quite compensate for the group delay dispersion correctly. Is the same true for the adiabatic fiber taper? Is there a better geometry than a linear taper?
Oh yeah, so good question. So the folks who are good at doing tapering say one can put a highly nonlinear function on it. In fact, there's this great animation of how they do it at Bath, and actually there are commercial devices to do this now. It's basically like a blowtorch that you're just kind of moving around, and you're putting tension on both sides. And depending where the blowtorch is where you have the ability to stretch. And so with they sort of move it around. I don't actually know if they're dithering or if they're moving it straight, but they can make highly nonlinear tapers. So whether that will actually work out is something we haven't checked. Yeah, but it.
I think there's still one more over there. Yeah, go ahead.
Fundamentally, what limits the bandwidth of the adiabatic frequency conversion?
The adiabatic one, fundamentally what's limiting it? Either running out of quasi-phase matching condition to work out, or running out of manufacturing capacity to go to a smaller polling period, or in a quasi-phase matching crystal. It's really, just in practice, if you can't phase match a certain wavelength in a normal process, then you can't do it with the adiabatic. But the cool thing about the adiabatic process is that you can do it all on one device if you can go long enough, right? If you make your device longer and longer and add more and more periods to it, as long as you don't have like group velocity walk off or something else that's getting in the way of propagating longer.
So I have a question on the chat now.
Okay.
You want to read through?
It says on the slide when you showed your trial experiment with conversion from 2 to 3 microns, could you make it work with third harmonic generation? Hey, a cool question. So actually, I had a great undergraduate RU student working exactly on this problem. He's actually going to give a talk at Photonics West. That's, I guess, probably the first that we'll publish this, but it involves 3 processes happening simultaneously. If a wave is doubled to its second harmonic, then doubled to its fourth harmonic, and it can be mixed with the fundamental to make 3 omega. But the normal route that people would take the third harmonic is suppressed, so omega plus 2 omega cannot happen. This also has a behavior of basically an asymptotically kind of damping out. And this is something that you could actually try to implement with a superlattice type of quasi-phase matching procedure. And it's something that he figured out one could do. So just one word about it, it's a lot better than trying to do simultaneous omega plus 2 omega in a crystal to make a third harmonic. But, you know, doing it in separate stages, the way folks at LLE, for example, do it, you can get such great conversion efficiencies that, well, at least, you know, we're scratching our heads, how important is this effect, but maybe we could talk sometime if you're interested in this third harmonic generation process.
All right, I think we should thank Jeff.